As we start these next couple of lessons on using the first and the second derivatives to help us understand function graphs, we need to make sure that we understand and remember the unit circle and how to solve trig equations. Let's do a quick little review of the important values that we see on the unit circle. On this chart, I've got a couple things. On the far left, we've got the important reduced radians that you'll see on the unit circle. For example, pi over 6, pi over 4, pi over 3, pi over 2, and pi. When I say reduced radian, I would mean something like, for pi over 4, anything that would involve a reduced fraction that would have pi over 4, such as pi over 4, 3 pi over 4, 5 pi over 4, etc. And in each of these columns, I've got the sine, cosine, and tangent values for these. It's going to be important that we remember the patterns that we see on our unit circle and how we might use them. So, for example, at pi over 6, or any similar sort of fraction, we will see sine equal to 1/2 or negative 1/2, cosine equal to root 3 over 2 or negative root 3 over 2, and tangent equal to root 3 over 3 plus or minus. As we go along, you'll notice that the sine values, as the radians get larger in our unit circle, also get larger to the point where we've got 1/2, root 2 over 2, root 3 over 2, and then as we've talked about in class, root 4 over 2, which is 1. And down here we've got all of our multiples of pi, which I kind of had to put in a separate little line there. Cosine values, as the first quadrant reduced radians get larger, get smaller. So as we notice at pi over 6, cosine is equal to root 3 over 2, cosine is equal to root 2 over 2 at pi over 4, 1/2, and 0. And then tangent, of course, is sine over cosine. You'll see these reduced fractions in here. We've got root 3 over 3, 1, and root 3. If you remember, tangent is the slope of our angle on our unit circle. So as our radians get larger in our first quadrant, the tangent values also get larger because the slope of the angle is getting bigger. And of course, at any multiple of pi over 2, where the numerator is odd, then we're going to have tangent not exist. Okay, so this will be useful as we go on. I've decided to show you an example of what it means to solve a trig equation with a relatively complicated one. So let's take a look at that. Our problem asks us to find where 2 sine of 3 theta plus 1 is equal to 0. Whenever you're solving a problem like this, we've got a little bit of a difficulty by having an input of 3 theta as opposed to just a regular theta. As always, though, the first thing we want to do is make sure that we isolate our sine of 3 theta, or our sine of whatever it is, or whatever our trig function is, so that we can actually go to our unit circle if possible. When we isolate sine of 3 theta, we start with our first step and get 2 sine of 3 theta is equal to negative 1. Sine of 3 theta is equal to negative 1/2. Now this is where our unit circle is very useful. So in our second step, we want to find wherever sine is equal to negative 1/2, ignoring whatever our input is. If we remember from our chart previously, we find out sine is equal to negative 1/2 at 7 pi over 6, which is the third quadrant angle in the pi over 6 family, and 11 pi over 6, which is the fourth quadrant angle in the pi over 6 family. We notice that we add 2 pi k to this. It's important that we keep that because we're going to get a solution every time we go around the unit circle backwards or forwards, and k is an integer. Next, we want to make sure that we set our input equal to those values we just solved and we just found on our unit circle. So what we do is we set 3 theta, our input, equal to 7 pi over 6 plus 2 pi k. When we solve that, we get 7 pi over 18 plus 2 pi over 3k. In some circumstances, it'll be okay to leave your answer like this. It all depends on whether you're asked to find particular answers on a certain interval. In our second branch, we had 11 pi over 6 as a possible unit circle solution. So we're going to set 3 theta equal to 11 pi over 6 plus 2 pi k. When we divide by 3, we end up with 11 pi over 18 plus 2 pi k over 3. Again, sometimes it's okay to leave your solution in this form. It depends on what you're asked for. So let's say, for example, you needed to find the solutions on the interval 0 to 2 pi. You're not just going to get with the answers of 7 pi over 18 and 11 pi over 18. Because the original equation had sine of 3 theta, you're going to have potentially 3 times as many solutions as you normally would. Okay, so when we start with that, what the plus 2 pi k over 3 means is that we need to make sure that we're going to add 2 pi over 3 to get every next solution that's possible on the interval. Notice that 2 pi over 3 is equal to 12 pi over 18. So let's start with the 7 pi over 18. When we add 2 pi over 3, or 12 pi over 18, our next solution will be 19 pi over 18. Notice that that's still less than 2 pi. And 31 pi over 18, which is also less than 2 pi. If we add another 12 pi over 18, we're outside the interval that we want, which is 0 to 2 pi. Now, let's take a look at 11 pi over 18. If we add 2 pi over 3, or 12 pi over 18, our next solution will be 23 pi over 18. And the solution after that will be 35 pi over 18. Again, adding another 12 pi over 18 will put us out of the interval. Students oftentimes mess up the most on these trig equations by not including the appropriate amount of solutions. Okay, you need to make sure that you're watching out for extra solutions that you might have because there are coefficients that are inside of your input. Okay, in this case, notice that we get 6 solutions, 3 for each original possibility.